Alright, so one of the most confusing things that we reach at this point in the course is the difference between alpha and beta glucose. As you can see with these two models right here, they're kind of hard to tell the difference in between. But if you look closely enough, you can tell the difference. And this is important as alpha glucose is what makes up a lot of the starches that we eat, so like the amylose and amylopectin that's in a potato. If you've noticed, you can eat a potato and break it down, and french fries aren't that great for you. Whereas with beta glucose, it makes up cellulose, which is a part of plant cell walls. We cannot break down plant cell walls, but certain bacteria can. So cows that have special bacteria in their gut are able to break down cellulose and get their energy from just eating grass all day long. Thankfully, we can't do that, and salads are relatively healthy. So, to tell the difference between alpha and beta, you want to track where the hydroxyl groups are. So on this drawing here, you can see that the alpha has hydroxyl on the bottom, bottom, top, bottom. So I like to think down, down, up, down. I can even draw that here. The alpha glucose likes to have down, down, up, down. So looking at this model over here, we want to orient it in the right way. We see the oxygen that's right here, and we see the big clunky carbon containing group that's up here, right there. And then we look at it and we see the hydroxyl on the bottom compared to the hydrogen. So we have down, down, and then this one is up compared to the hydrogen, so up, and then it's back to being down. If you're holding one of these models, an easier way to do this would be to look at the hydrogens. You see up, up, down, up. So this is an alpha glucose, which goes down, down, up, down with the hydroxyls. You can also look at the hydrogens. So looking at the beta glucose, we see more flip-flopping. We see up, down, up, down, up, down, up, down. Right? So we orient it in the right way, and we have oxygen, and we have the carbon with the big clunky carbon group, and a hydroxyl group right there. And we orient it, and we see hydroxyls up, hydroxyl down, hydroxyl up, hydroxyl down. So we have up, down, up, down. If you look at the hydrogens, we have down, up, down, up. Right? Beta glucose. Alright. So typically with the beta glucose, I like to think, okay, the different groups are flip-flopping, and the beta kind of looks like a flip-flop if you pretend hard enough. So that's pretty good. So if I bring in this other one, are you able to tell me what it is? So we start with it like here, and we want to orient the oxygen like such, and we have the big carbon group right there. So based off of the hydroxyl groups, what could it be? Is it alpha or beta? I'll tell you. So we have the hydroxyl, it is down. We have another hydroxyl, it is down. So right now we already see that the hydroxyls aren't flip-flopping perfectly like the beta, so this is an alpha. We have down, down, up, down. So this is an alpha glucose. Alright, so with our two alpha glucose molecules, we're going to try and make a maltose, which, unlike alpha glucose, which is a monosaccharide, maltose is a disaccharide because it's made of two alpha glucose monomers. So specifically, we want to find the one carbon on one alpha glucose and the 4 carbon on another. So whenever we're naming carbons, we're going to hold it like we did before, and then we're going to count clockwise. 1. Wait, nope, this is wrong. Oops. There's the oxygen. You always want this big clunky group to be over to the left. This is going to be your last carbon. So it's going to go counterclockwise or clockwise. We're going to go 1, 2, 3, 4, 5, 6. So that's what you should remember. This one hanging off is always going to be your 6th carbon. So 1, 2, 3, 4, 5, 6. Or your last carbon. It's different with pentoses. So this is our 1 carbon. We're going to keep that. And then looking over at the other one, we're going to do the same thing. Orient this. This is your 6th carbon on a hexose. So here's your oxygen. 1, 2, 3, 4, 5, 6. So we want the 4th carbon. 1, 2, 3, 4. So here's our 4th carbon. Here's our 1st carbon. We're going to link them. We have 2 hydroxyl groups hanging off the end. If you recall, we're going to do a condensation reaction. So we're going to form a water. So it doesn't really matter which one you use, but you're going to leave an oxygen in between. So you pop off a hydrogen. That hydrogen forms with the hydroxyl group, and you have a water molecule. It's condensation reaction because we're losing water. And then this forms a bond. Boom. There it is, 1 maltose molecule. Nice and big and probably yummy and sweet. So this is maltose. What is the name of this bond that's formed in between? For carbohydrates, it's going to be a glycosidic linkage. Right? Glyco, sugar, linkage, they're linked. Easy enough. But we want to specify which carbons. So we had a 1 and a 4. So it is a 1,4 glycosidic linkage. So that's that. You made a maltose with 2 alpha carbons. So the important thing is to note that alpha and beta glucoses are different. We can digest polysaccharides of some, but not others. Yeah.